Hello, my name is Leah Alexander. I'm a rising junior at Purdue University studying materials engineering. My project was on thermal behavior improvement and supercooling suppression of inorganic phase change materials. I quickly want to thank the sponsor of this project, online O-REU program at Texas A&M, and the collaborators, Professor Svetlana and my graduate student advisor, Parvin. So the reason why I'm looking into this is because each year humanity's energy use increases and we need to start looking at where we can substitute renewable energy sources into where fossil fuels are currently used. And phase change materials offer a potential solution, but they all have ups and downs that need to be addressed before we can properly utilize them. And so I started consolidating current research on inorganic phase change materials. So a phase change material is a material that has a large absorption or release of energy during a particular phase transition, often between the solid and liquid phase. So you can see over here that the material starts off as solid and will melt and absorb a bunch of energy and go into the liquid phase, and then it will eventually release all that energy during the solidification process. And we want to capitalize on that latent heat storage. There's a lot of different phase change materials, main categories being organic, inorganic, and eutectic. And for the purposes of this study, I focused on the salt hydrates because of their particular set of properties that were intriguing. The main positives of inorganic PCMs that make them a desirable material are their high heat storage density, higher thermal conductivity than organic PCMs, and the fact that they are non-flammable, unlike organic PCMs that are flammable. However, they have significant problems of supercooling and phase separation, as well as being corrosive, and all those problems need to be tackled in order to improve their utilities. Current uses for them include medical devices like this heat pack over here, as well as solar heating systems, textiles, cooling electronics as well. For the purposes of this study, I did a deep literary analysis on what's currently available on inorganic PCM. So I first started with understanding the topic and getting a general overview on the material. And then I moved on to what's currently being used to tackle the supercooling problem of inorganic PCMs and what new solutions are potentially out there. And then I looked on how support materials aid in shape stabilization and reducing the supercooling problem. And lastly, I looked at what potential novel solutions can be investigated to both aid in shape stabilization and supercooling. Supercooling is when a material cools below its phase change temperature without going through the phase transition. This is a typical thermal cycle of a PCM where it heats up, goes through the phase change, and heats up some more, and when it begins to cool down, instead of going through the phase transition at this specific temperature, it continues to cool further until it finally does go through the phase change. It jumps up in temperature, experiences the transition, and cools down again. This reduces the effectiveness of the PCM because it's not going through the phase transition at the desired temperature. The typical way to combat this is using nucleating agents. However, I also looked at the potential of using polymers. Nucleation agent is an additive that allows the material to start going through the nucleation process. And in order to find an effective nucleation agent, you have to know two things. First one is what growth planes of the PCM allow for growth in every direction. And then you need an agent that has a small lattice mismatch to that PCM's growth plane. And by doing this, you reduce the surface energy equation, you reduce this term. Reducing this term reduces the entire surface energy equation. By reducing the surface energy, you reduce the activation energy needed to start nucleation. You can see in this graph down here, these triangles represent different nucleation agents. And the ones that had very small lattice mismatch had reduced the supercooling from 40 degrees down to below 10 degrees, whereas nucleation agents that had more lattice mismatch did not reduce the supercooling nearly as much. So a potential avenue to explore is how polymers can add in nucleation sites into salt hydrates. In particular, I looked at polypropylene oxide and polyethylene oxide. Both of these have an ether oxygen on them, and that's a polar functional group. And what it does is it pulls in the metal cations from the salt hydrates and starts a nucleation crystal, which kicks off the nucleation process. In addition, they have a hydroxyl group at the ends of the polymer strains. However, this hydroxyl group, while it interacts with the salt, can also interact with the water molecules, and we don't want it to interact with the water molecules because it will pull water out of the solution and just exacerbate the phase separation problem. In addition, I saw that PEO was more effective at starting nucleation crystals than PPO because PPO has a methyl group right here that reduces access to this ether oxygen. So in particular, we want long linear chains of polymers that have easy access to the functional groups. Other ones that I looked at were polymers that had phospholine groups and cyanide groups. And both of these were able to reduce the surface energy for hydroxyapatite, a salt that is found in bones. And it shows that the polymer was able to reduce the surface energy, so it reduced the activation energy required to start nucleation. The most promising one of these all is ones that contain the cyanide functional group, because while this does have a polar property and interacts with these metal cations in the salt, it does not have interaction with water, which is very promising. Phase separation is a significant problem experienced by salt hydrates. They often separate and the salt precipitates out of the solution. This reduces the number of thermal cycles a PCM can be used for. In addition, they have low viscosity in their liquid phase, almost like water. As such, support materials need to be added into the PCMs to prevent these leakages and phase separation, and this is what shape stabilization is. Lots of different potential support materials have been explored, such from metal foams and expanded graphite to minerals and silica, and all of these have positives and negatives. Metal foams and metal organic frameworks, while both having high specific strengths and high loading factors, can often lead to leakage, and because of the corrosive nature of inorganic PCMs, they aren't quite valid for these materials. Carbon nanotubes and graphene have very high thermal conductivities, but they have very low loadings, so you can't add as much of the PCMs into them as you would maybe like. Two of the most promising ones for inorganic PCMs currently looked at are expanded graphite and porous silica matrices. Expanded graphite has high thermal conductivity and low density without very much problems, and silica has high specific surface areas and tunable pore sizes, but they don't quite add into the thermal conductivity like expanded graphite does. Looking more into the effects of a silica matrix on hydrated salts, you can see in this study here they used a mixture of 2 hydrated salts, as well as tested a coated composite that was coated with a paraffin wax versus an uncoated composite. The coated composite had a higher latent heat energy than just the traditional hydrated salt mixture, which is a promising aspect to adding a silica matrix, as well as the coated and uncoated composites were thermally stable for 10 cycles, whereas the hydrated salt experienced a decrease in the thermal capabilities throughout the 10 cycles. Interestingly enough, the coated composite was better than the uncoated composite because the coating prevented water loss during those thermal cycles, as well as reduced interactions of the salt hydrates with the silica matrix that can affect the thermal capabilities of the salt hydrate. And expanded graphite being another support material of interest, they tested this with sodium acetate trihydrate and a formide mixture. And you can see that the pure salt hydrate mixture experienced more supercooling than the mixture when it had a 5 weight % expanded graphite added into the composite. That greatly reduced this divot right here and had a more even phase transition with minimal supercooling, a very promising thing to see when adding expanded graphite. In addition, the thermal cycle was stable for the 10 cycles that this composite was tested for as well. So my recommendation after consolidating all of this information is to perhaps look into polymers with cyanide functional groups. This offers a solution to the supercooling without adding a nucleation agent because of the interaction of the salt ions with that cyanide functional group. In addition, look into the gelling of polymers to increase the viscosity of the PCM. By increasing the viscosity, you can reduce the leakage as well as how much the salt will precipitate out of the solution, effectively increasing the number of thermal cycles experienced by the PCM. and make an effort on seeing how you can combine solutions for both supercooling and shape stabilization into one. Thank you very much for listening.